The next type of bifurcation that I'd like to present is known as the pitchfork bifurcation. In fact, there's two different types of pitchfork bifurcations, and I'll first focus on the subcritical pitchfork bifurcation. Such a bifurcation arises in the generic way in the following equation motion: x dot is equal to rx plus x cubed, where r is the control parameter in the system. And as we'll see, as we change r, we can go from a situation with one fixed point to three fixed points, or vice versa. For this equation, the fixed point values are x star is equal to 0, and they're also equal to plus or minus the square root of minus r. So to see this in action, let's plot x dot as a function of x for the three cases where r is positive, negative, or equal to 0. And let's first of all look what happens when r is negative. Well, when r is negative, then we see that we go through the origin with negative slope, but for large x, this function blows up to plus infinity, so there has to be some fixed point, a non-trivial fixed point or non-zero fixed point for positive values of x. And if we just plot this function, we'll see we get a cubic function that looks something like this. And from the slopes at the fixed points, we can immediately infer that the fixed point at minus root r, that's an unstable fixed point. At the origin is a stable fixed point, and at plus square root of minus r, there is a stable fixed point. So our flow diagram looks like this. When r is equal to 0, then the function it's just a cubic that goes through the x-axis only once, and so our function looks something like this. It goes to the origin with 0 slope. There's a non-linearly unstable fixed point, because to the right of it, x dot is positive, and so the flow is to the right, and to the left of the fixed point, f of x is negative, and so the flow is to the left. And finally, when r is positive, then we go through the origin with positive slope, and then we're taking off with a cubic nonlinearity, so we have a function that looks something like this, for example. And so this is an unstable fixed point with rapid flow away on either side. And so once again, we can look at the bifurcation diagram that's induced by this type of bifurcation. So let's plot as a function of x star. So for r positive, the fixed point at the origin is unstable, so that is this green dashed line. For r negative, the fixed point at the origin is stable, so again we represent that as a solid green line. So this is the unstable fixed point, so this is the stable fixed point. But in addition to that particular fixed point, we see that because this is a cubic function, there are two additional fixed points, and they are both unstable when r is less than r star. So there is these two unstable fixed points. And now we can fill in the flow pattern that's induced by this bifurcation diagram. We see that when r is positive, we have the unstable fixed point, and so the flow is always pointing away from the fixed point. For r negative, then the flow inside the parabola is pushing us towards the fixed point, opposite to what happens for r positive. And outside the parabolic region, the flow is again away from the parabola itself. And so here is the bifurcation diagram associated with this flow pattern. And once again, the values of these fixed points are located at minus the square root of minus r and plus the square root of minus r. Why this is called a pitchfork bifurcation is suggested by the diagram itself, because as we go from r positive to r negative, we see that the middle tine of a pitchfork changes from an unstable to a stable fixed point, and we generate two additional tines of the pitchfork. That's why it's called the pitchfork bifurcation. And why it's called subcritical is that when r goes less than a critical value, r equal to 0, is where we have the pitchfork actually appearing. One last point I just wanted to emphasize for all of these bifurcations that I've shown so far is that even though I've given you a very specific form of the equation of motion, this is the generic form very close to the bifurcation point itself. As we'll see in specific examples, the types of bifurcations will have very different equations of motions, but when we look very close to the bifurcation point itself, this is the canonical form of the equation of motion that occurs.